Okay, Estefania and Amy, you have joined, and so we're on live for a quick review session. So I think the way I have hoped this would be is that more of the class would join, but seems to be not the case. Can you see my screen?
Yes. Yes, we can see it.
Okay, fabulous. Okay, Shanice, hi, there's Shanice. Okay, the way I was hoping we would do this is by you basically letting me know what the specific interests are or what specific questions you have. Are there specific questions? If anybody wants to go first. Was everyone okay? So let's start alphabetically. Amy, do you have a specific question which you would be interested in?
I don't have any specific questions. I'd really just like to see like everything happening in action so that it kind of sticks to my memory better for when I do the practices and do the quiz. Mm-hmm.
Sounds good. Okay. Okay, thank you, Amy. Estefani, any specific questions from your end? Any particular topics that you want to review from the lectures?
Just like Amy said, more like doing it live. I feel like reading it through like the textbook, not the textbook, the spreadsheet and the lecture. I was having a hard time going back and forth, but I'm binomial and the normal thing, that would be great.
The binomial distribution specifically, so that was in session 2, right?
Mm-hmm. Yes.
So what specifically is your question in this regard? Okay, so binomial distribution in principle, so you're having an outcome that is either success or failure, right? So you have a coin flip, you have survival, yes, no, or you have a treatment outcome, success or failure. And that's also hand in hand with one of your colleagues that essentially also asked the same question, how that actually relates to the normal distribution. Is this kind of where your main interest goes, Stefani?
Yeah, that's part of it.
Okay. Okay, so let's review the slides quickly, and then along these lines, you can ask additional questions. So essentially what we have is we have an outcome variable that is either 0 and 1. The probability of PYI equals 1, so where this y is actually 1, is here the P. And the probability of yi equals 0 is 1 minus P. So it adds up to a total of 100%. So either you have an outcome or you don't have an outcome. So it's basically one is the actual outcome, the probability of that outcome to happen. The other one is the inverse of that outcome to happen. So if you have now repeated samples being drawn, this probability essentially is then cumulative. So it's a binomial distribution, right? So you have this probability that essentially follows a certain kind of outcome, which is relating to the number of trials that you essentially have used. So it depends how often you flip that coin. You basically have these independent trials, and all of them basically have a certain kind of probability of that outcome to happen. So this probability, this cumulative probability over several trials will be between 0 and 1. You would expect with large numbers, with a large number of trials, you would expect this estimated probability or model probability to be equal to the probability that you have estimated in the beginning. So if you want to put this in the concept of a trial, for example, so you have a probability, you have a prevalence of 10% of diabetics in the population. And you're basically drawing a random person from this population. You have a 10% chance that you're drawing a diabetic. And this may not be true when you do one person, but if you draw, let's say you have the population of New York City, let's say you draw 1,000 people, this will basically shape towards that real P, that real prevalence to be true. So you will likely have, with a large number of 1,000, you will have something that is very close to 10%, which would be 100. So this is the expected probability, so to say. This is this expected X bar, right? So going on, so you can arithmetically approach this in various ways. So you have the number of trials, you have the probability of successful trials. So that actually is now when you bring this into practice, and you have done this with binom.dis, that you have seen the actual probability examples, right? So you have with 4 patients, you have 4 different outcomes with these 4 patients. So you have a probability, you have 4 trials and you have 0.75. You can, if you have seen that spreadsheet that I have posted, you can easily also arithmetically approach this by looking essentially at, with binom.dist, you can look at these exact outcomes. So if you have a probability here, back to my 10% prevalence, and you want to know what is the probability that you have exactly, let's stick with 3, which is you have with binom.dist, you come to the number of trials here. So you have the number of trials, which essentially is here the B. No, that's number of successes. That's 3 successes. Then you have the number of trials, which is 4, which you can change in the formula. Then you have the probability, that's your prevalence. And you have cumulative yes, no, which essentially here is no, but you can also change this to cumulative true. Then you would basically get a cumulative estimate. So then there was the distinction between at most and at least, but we'll get to that later. So this X, this outcome basically varies with each time you draw from your population, right? So it's either successful treatment or non-successful treatment. So let's continue. So assuming independent trials, the probability will either be a success, n minus x equals 4 minus 1. So you basically have 3 failures whereas 1 success. So you would cumulatively estimate the trial, the success, where you basically have a probability of success of 0.75 multiplied by 1 minus failure by the power of 3. So this basically will give you this outcome where you have 1 positive and 3 negatives. You have 1 positive. So this is the constellation, and that's basically where you need to approach this in this form and fashion. So this gives you a probability of 0.05. So this is basically how you approach this arithmetically, and binom.dist basically does this work for you and solves this for you. So now there are more examples. Let's skip over those. So you basically, binomial distribution is the number of scenarios multiplied by the probability of one single scenario to happen. So if you have a large n, and this comes now back to my example, so you can do this factorial by basically approaching this with each repeated measure. This would be like you would use binom.dist. If you are, so this is the formula, but now we want to come to the binomial distribution and how this relates to the normal distribution. So if you, oh, where's the slide that I'm actually looking for? Okay, so if you have a large number, so you have a large number of individuals that you're drawing, you have a certain probability to happen. You basically assume that you are drawing with each trial with a certain probability. So let's say you have a large population and you're drawing a certain sample from that. You will have in each sample, you will have a certain prevalence, which essentially is then found somewhere in this normal distribution curve, meaning you have a certain prevalence or a certain proportion of individuals with your with a certain condition in your sample, and this will essentially distribute in a certain shape or form. So let's if we're using Okay, the Facebook example is we have 25% of Facebook users are considered power user. Same study found that the average of Facebook users is 245 friends. What is the probability that a Facebook user with 245 friends, that 70 or more friends would be considered power users? So we have an N of 245 and we have a P of 0.25. So if you are now from these 245 people, you're drawing now, let's say you draw samples of 10 or samples of 20. You get out of these, you get a certain proportion of super users amongst these smaller samples. So this prevalence estimate could, for example, be situated somewhere around this 0.25, and you're finding a certain probability that that distributes around the real prevalence of your population. So you take a sample, you find a certain prevalence, then you put that sample back, you draw another sample, you get a certain prevalence, and this prevalence will be distributing around a prevalence, and this forms this normal distribution. So each estimate, each sample estimate, each sample prevalence situates and basically centers around the real true prevalence of your population. So in a totality, once you have drawn several samples and you have drawn with a certain probability, you will get this probability estimates that all in its totality will essentially reflect the true population proportion. And these estimates that basically are not are somewhat deviating from the true population will basically build the shape of the normal distribution. So this being said, that's how you get this mean reflecting the true population prevalence or the real true population proportion, and the estimates that are deviating from this true population proportion building up the variability around this true population proportion. And this is basically reflected. So this is the true population proportion, whereas this is the essential standard deviation around that. So this is not a proportion. I think it would have been easier to kind of show this using a proportion. So you have 0.25 essentially gives you a mean of 61.25 super users in your population. So that's 0.25. So this 61.25, which is basically the center of this normal distribution, is reflective of 0.25 proportion. So you have drawn repeated samples, and each of these samples gave you a different proportion estimate. And these samples reflect now an estimate of the true population proportion of the 245. But you've drawn smaller samples in order for you to estimate the true population proportion. And so now this explains the shape of the normal distribution. So this being said, your probability estimate for one individual essentially is here being set as a mean of your normal distribution X estimate, which essentially you assume to be consistent with the prevalence, and your oops, no, that's not good. And then you're taking the shape of the normal distribution to assume that this will build the variability around your estimate based on your sample estimate. Was this somewhat clear, Stefanie?
Where where did you get the 0.75 from?
The 0.25 from here. Yep. So we have 25% Facebook users are power users. So the average Facebook user is 245 friends. So what is the probability that the average Facebook user with 240 friends has 70 or more friends? So we have an N, which are our trials, and the probability of 0.25.
So yeah, but the 0.75.
No, it's 0.25. Did I say
If you go
75?
back, if you go
Stephanie,
back,
I think you mean for the sample
yeah,
mean?
Yeah.
The sample mean here is 61.25.
And then it says 245, then 0.25
Yes.
times 0.75.
Yes, that's, yeah, hold on. This is this formula there. So we have
Okay.
here the mu. So this mu is the true population proportion. And you mean to estimate it with your sample. So you have 245 multiplied by 0.25. So these are the ones that are actually power users. And the normal distribution always has like a center, and it has a variability. And the variability is the standard deviation, right? And this standard deviation can essentially be calculated with the square root of n, which we know is 245, multiplied by p, which is the 0.25. So these are the power users, multiplied by 1 minus p. And this is the failure. So if you translate it now into success and failure, p represents the probability that you draw a super user, whereas 1 minus p is that you draw a non-super user. And this is basically allowing you to characterize your normal distribution around your repeated samples that you have drawn. And with each sample, you get one estimate. This distributes around the true population mean. Does that make sense? Does that make it clearer?
Yes.
Yes?
Yes.
Okay,
yes,
great.
yeah, I understand it better. Thank you.
Great. And essentially, this is Binomial Dist, essentially goes essentially and does the actual real calculation with the factorial approach, right? So it really calculates. Okay, so this is what we saw before, the formula with the factorial approach. Binomial Dist is actually calculating the factorial approach, the real approach. But this normal approximation is very helpful when you have, for example, an estimated proportion given, and you want to understand what are the confidence interval around, or what are the actual variation around this estimate. And with what certainty you can actually observe that. So once you essentially have this normal distribution characterized with your standard deviation and your mu, then you can basically employ exactly this equation to basically assume it's a normal distribution. And based on this normal distribution, you can then use the calculation of the set score and use with the set score to actually calculate what is the probability of an average Facebook user with 240 friends that he has 70 or more friends. So now you have the average Facebook user with 61.25. So this is the 0.25. And now you have one with a 70 friends as your circle of friends of interest. And you're locating now your 70. You're subtracting the mean from it. And by that, you basically get the difference between your observed minus the mean. So this is like 8.75. You divide it by your estimated standard deviation, and by that you get 1.29. And then it really follows the approach that you basically know from the normal distribution. And you get 0.9015 from the set score table. Since you're interested in greater than this point, you basically have to subtract this 0.9015 from 1. So you calculate 1 minus 0.915, and you get to 0.0985. Does that explain how a binomial distribution relates to normal distribution? Because that's quite an important step and kind of an interesting thought process to how you essentially get to that. So the key is really that you're drawing samples, and based on these samples, you essentially have a certain risk, and there's a relationship of that risk or probability to estimate your true population mean. But having repeated samples gives you a distribution around this true population mean. But the center essentially should be a reflection with large numbers of the actual population proportion or population risk, so to say. Does that make sense, Estefany?
Yes, thank you.
Yeah, okay, great. Any other questions? Shanice, let's go continue.
Questions. I just joined to see it live.
Okay. Excuse me. Welcome. Okay, Caroline, do you have any questions? Was my Excel example helpful in regards to understand the binomial distribution function?
Yeah, it was, especially the email, which I posted on the discussion board. And
yes, I've seen that. Thank you. Thank you for that. So I think it's a very important function to know and to understand, because this is really how you operationalize the estimates in Excel. And that really allows for you to get to these estimates, right? So to the other on the call, have you all seen the discussion board entry, the question that Caroline has posted? So the specific question was, what is the difference between exact and cumulative? And essentially the difference is that exact gives you the probability for this exact success count, whereas cumulative essentially adds up to, so you have either you can cumulatively approach it as cumulatively at least. So then you have this estimate and you're calculating everything above that. For that, you need, just in the context of this equation, you need to calculate 1 minus this estimate. If you have at most, then you're basically calculating only up to that point. So essentially, it's making advantage of this very same dynamic and characteristic of the normal distribution curve and the estimate of the population proportion. So at most basically goes from the point on the very left up to that point of interest, whereas at least essentially moves from this point of interest up to the very right point. And in arithmetic terms, you basically calculate 1 minus binom dist, whereas here you calculated binom dist from left to right. Any other questions for me, Caroline?
No, it's just that one. So 1 minus the sum would be if it's from
the point to the right, yes.
Yeah, okay. All right.
So that defines at least and at most, right? So this is why I specifically meant to show the difference between at least and at most. And I think this is how you arithmetically really can kind of derive what is being meant. And I highly recommend to actually really always kind of draw out the normal distribution curve. And by that, essentially get an idea of where things are located. It makes it easier conceptually to grasp what is essentially being looked at. Good. Okay. Thank you, Caroline. Then we have Spreza. Am I pronouncing it correctly?
Spreza. Thank you.
Spreza. Okay. So you had some problems with SPSS. Hopefully these were resolved.
Actually, yeah. Today I finally got it like a couple hours ago. So I gained access in a totally different way. So
okay. But it's working now. Okay, good.
It's working. I'll be okay from tomorrow on with SPSS.
Okay, sounds great. Sounds great. So everybody else having problems with SPSS? So I think one of the easiest way to essentially use that is by really using the virtual desktop. So I found this to be quite a good functional version. So SPSS, it's not my software of choice. So I'm an R user. So I'm not super savvy in it. I find my way around it, but it's so you will later on find R to be another software that you will be exposed to, which is kind of entirely different. So are there any questions in terms of the functionality of SPSS at this point? Or were you all able to explore the data as being asked for?
Yeah.
I have a question from Spreza. Is it exact equals false and cumulative equals true when you put in? Whenever it's no. So to your question, it's not when you put in binomial dist and prevalence true. Whenever it's cumulative, no matter whether it says at most or at least. No, it's not. So it really depends on the direction you're looking at. Was my explanation before sufficient? Helped you to understand it, or do you want to walk through it again?
I'm not sure, like when you're putting it into Excel,
Mhm.
like I can work it out by, like I worked it out on paper, but when you
Yeah.
put it in Excel, like how do you, like how would you know when you're putting a cumulative for an at most statement or like a at least statement?
Yeah, so you gotta look at it from that angle, that you essentially you go up, you have 4 trials, right? So this is a simple example, like you have 4 trials, and you can either have no correct count, so no success. You can have 1 success, 2, 3, or 4 successes at the very most. Right, if you have at least, you want at least 1, that means you have 0 and 1, right?
Mhm.
If you have at most 0, you have equals the exact of 0. So this is you have at most 0, that basically means you have 0. If you have at most 1, you have 0 and 1. If you have at most 2, you have 0, 1, and 2. So now reverting to something, looking at the inverse of that, essentially if you have at least 1, that means that you have at least 1 would be 1, 2, 3, and 4, right?
Mhm.
So this is also where you essentially you have the highest value with at least, because your prevalence to actually draw 1 individual is essentially 10%. So if you come from 1, you have to take the inverse of that. So you go from the left to the right. So you go to your success probability, and then you're inverting it by calculating 1, which is the entire shape of the norm distribution, and you take everything exceeding this probability. Does that make sense?
Yeah, I think so.
Yeah, okay. That's not convincing. So you
You know what? It's a long day. It's familiar from what I was doing yesterday, but it's been a long day. I've been doing a lot of Zooming.
yeah,
I might
I
just
hear you.
hit the max of my potential
Yeah.
right at this moment.
Yeah, it's the same for me. This is how these are like this on Zoom, right? So you have, yeah. So at least means you have 1, 2, 3, and 4. You're basically getting the probability of either of these occur. So when you have a probability that is actually of 0.10, a prevalence of 0.10, you have here a smaller probability to actually have 2, 3, and 4. So and that basically decreases because you actually have a low prevalence, right? So you have from your entire population, your P is actually only 0.1. So from that point, essentially, you decrease the probability to actually have more successes with a low probability. Does that make it a little clearer? So this is basically, so you need to, at least you're basically going from the probability estimate to the right. And for at most, you're basically capturing everything below that desired success count that you're looking for.
Yeah, I mean, that makes sense. But when you're putting it like in the, can you like just click on what's the difference between like what you put into the cell to get these like cumulative versus cumulative sum? Like, I mean, the at most and the at least, what's the difference in like when you're putting at the end? Like you put true because they're
Yeah.
both cumulative, but like what's
Okay.
different in the setup? Is
So
it,
the difference in the setup is, and this is why I put these both in there in the same way, because when you look here, you have at most 0. That means you have exactly 0. So this is why this cell corresponds exactly with the exact of 0.
okay.
If you have cumulative at most, you
Okay.
have 0 and 1, which is C6 and C5. If you have at most for 2, you have 0, 1, and 2. So you have C5, 6, and 7. So this sums up. And when you look now at the formula, you have binom dist. You take B7 as the success. You take the prevalence of 10. You take the trial count of 4. And then you give true for cumulative. So basically, it sums up everything up to that desired success count.
Okay.
And inverting that gets you to at least. So that's the trick,
Okay.
right?
It's just 1 minus and okay.
That is the way how you approach it. Yes,
Okay.
exactly.
All right,
Exactly.
cool. Thanks for
All right.
clarifying.
Okay, glad to hear. All right, Sarah, welcome. Do you have a specific question for me? Anything I can explain to you, hopefully successfully?
I don't know if someone already asked this, but I was wondering, we have the reference tables on the course Blackboard. Should we use just the Excel for the quizzes? Because I feel like I'm getting very close to the Excel answer, but like when I use the reference tables, they're a little off. So I'm wondering if I should look at the Excel or the.
That is a very good question. Let's look at it. So the difference is A, the way Excel is computing it, and B, it's often a rounding issue.
Right.
And that's actually something that is somewhat, wait, let me pull up one of those tables. So it's a rounding issue. I would think that, so there's a margin added, right?
Yeah.
So if you enter this in the quiz, I certainly will go through the quiz questions one by one. If there's really a problem because of a clear rounding problem, don't worry about that. You still get those points. But it's considerably point on, so it's to 2 decimals. But I think it's fair enough. I don't think you will run into a problem that there's a wrong flag for something that is just a rounding issue.
Thank you.
You're welcome. You're welcome. Okay, do we want to discuss any other topics? Any questions about histograms? I think that was now what we did in session 2 with histograms. Of note, whenever it comes to data analysis, histograms are really your friend. Always use histograms. Look at every variable, always in terms of histograms. Make sure that you really understand center, variability, ranges, min and maxes. This is really extremely important because you need to understand the shape of the distribution. You really need to understand whether this is skewed in any way or whether this is really something that qualifies for normal distribution. So it's particularly with smaller numbers, it's more of a problem. With larger numbers, it's pretty much everything qualifies as a normal distribution to some extent. And also histograms give you a good opportunity to also identify all potential outliers. Outliers are really a huge problem. You really need to identify all your outliers because that will affect your measures of the central tendency, particularly the mean, because that's arithmetically related to outliers, right? As soon as you mix an outlier in there, arithmetically there has to be a change almost. Also with large numbers, there will be less of a change, obviously, but there will be a change, arithmetically has to. So you have extreme skews, you identify, that's also important to keep in mind. All data that you see essentially can have a potential error. Always use kind of, we call it in my day job, we call it the sanity check, like literally look at the data, to what extent it distributes, what are the outliers, is there something that is really not possible to find in a patient? If you, for example, if you have blood pressures that are basically not possible to exist in a human individual, you can exclude those just on these grounds, or at least you will escalate it and you will make sure that you get the real number. And it provides interesting insights. Extremely skewed data is hard to calculate. Median, if you have skewed data, always use the median. Essentially, I think that was discussed. The way you will always present data is by using a mean plus minus a standard deviation. That's a very typical way of depicting data. So you would have mean plus minus a standard deviation. Whereas when you have skewed data, you would always present it with a median. And so that's my personal way of doing it. We talked this class about percentiles. I would do 25th and 75th percentile. And you basically, you're showing this in your report, in your paper. You would really report this data in that way and fashion. So it's a mean plus minus standard deviation, because you need the standard deviation basically only to display that there's a variability around your center estimate. And for that very reason, you assume it to be symmetric. Whereas with the median, you essentially get, so this is the 50th percentile, right? So you get the center based on the percentiles and irrespective of the distribution. So 25th and 75th percentile gives you an idea in which direction it actually skews, right? So because if you know the median, if you know the 75th percentile, you can actually see, okay, how far is my skew as compared to my skew in the other direction. And this is actually very powerful knowledge when you think about it. Also, what I always recommend to everybody is to always compute mean and median at the same time. If you do not have computed the histogram and you just compare mean and medians, that already gives you an idea whether this is a really nice normal distribution or it's not. Because the median will be considerably stable compared to the mean. The mean always has to change with outliers, whereas the median is rock stable. So, no, not rock stable, it's considerably stable, let's put it that way. So essentially you will have, by that, you will have a possibility to just numerically compare in which direction your data essentially shifts and skews. Then always do histograms, that definitely is also important. And with the mean and the median. Does anybody have an idea? So if you have a mean that is smaller than a median, in which direction is the skew?
To the left, or?
Yes, correct.
Okay.
Because you have outliers to the left that essentially pull your mean to the left, whereas the median remains stable. So very good, good thinking, Sarah. Okay, so this is mean, median. That's easy, right? Not a problem. IQRs, yeah. So you will find some other ways to depict medians. I personally don't like it for that very reason, because you lose a lot of information. So some reports present median instead of 25th and 75th percentile, you present median at IQR. I personally don't like that much, because you lose this information, right? You lose the distance from the median to 25th and median to 75th. So I would always recommend to use this way of depicting skewed data or non-normally distributed data for whatever reason. Then you have a box plot. We have seen that. That's a very elegant way to depict data and to also compare it against each other. So you basically have medians, that's your Q3, that's your 75th percentile, and your Q1. So of note, essentially, when you look at this way of depicting data, if you have a table and you have a corresponding figure, always make sure that you understand what the figure shows and to what extent you're representing your data correctly in your table, because this corresponds now with this, right? So if you have a figure and you have a corresponding table, make sure that you're showing a box plot always with median. I would not use mean versus a box whisker plot. Then you have the whiskers, $1 million question if you ever asked that question. So the whiskers essentially reach from Q3 1.5 times the IQR. So only outliers that exceeds this, so you have median, you have Q3, and Q3 plus 1.5 times the IQR. Only those outliers that exceeding that whisker will be depicted on the box whisker plot. That's sometimes nice to know because you will see outliers. And when it comes to outlier identification, this is one simple criterion to essentially employ. Whiskers, oh yes, written here. Okay, location, mean, okay. Okay, now if there are no specific questions, so this is the variance, then we have the variance, variance, standard deviation. We're doing calculations. We have normal distributions, the standardizations. Any questions about standardizations? Standardizations are really, yes, question? Okay, standardizations are really important because essentially you are not only being able to identify people or individual scores based on population, you can also compare apples with oranges because you basically can compare individuals who scored on one exam and you compare to a score on another exam. You can do this with various parameters. Doesn't always have to be exam scores, but it's sometimes helpful to have a way to depict it in that way and approach it in that way. All right, norm dist. I think these are the easy examples. So basically you can with norm dist, you basically get the distance from the left to the right. If you do 1 minus norm dist, you basically get from the point of observation from your x all the way to the right. This is important later when it comes to hypothesis testing. You can standardize it. These are the Excel formulae. Well, I hope you all went through these practice examples. So these are good practice examples to actually practice this. Then we have the empiric rule. So you basically you have 68% you have within 1 standard deviation, 95 within 2 standard deviation, 99.7 within 3 standard deviations. I think this is considerably easy. The QQ plots, this is always kind of important. So this is actually normal probability plot, but you can also do quantile plots to essentially depict normal distribution. So everything deviating from this line of identity here will essentially indicate it's not a normal distribution, just like seen here, for example, although this is considerably normal. Then we have the more skewed ones. So you basically see the left skews more to the left, but the right skews go more to the right. So that's all considerably simple. All right, contingency tables, important knowledge to have. Well, so I wasn't really meaning to go through the slides again. Are there any specific questions about anything? If there's something, I'd be happy to discuss something more in SPSS. If there are any problems with any of the analyses, were you all able to solve the problems that were being posed to you in the exploration examples?
Yeah, I didn't. Yeah, it was pretty easy.
Okay. Yeah, SPSS is considerably good to start for all your analysis because it's very user friendly. What's also important with SPSS, and please keep this in mind, you actually have also syntax that can be written. So every analysis that you do essentially also has its own syntax, and it's very useful. So you basically have SPSS, you have 3 main parts. So you have the SAV, so this is the file format that SPSS provides. You have in the file format or in the actual data format, you have variable views. You can make sure that all these variables are in the right format. You can change this format. You can also add labels. You have then for all analysis that you will be doing, you have so-called output files, and you will in addition to that have syntax files. I always recommend to kind of, whenever you run analyses in SPSS, I would always recommend to run them from the syntax, but we will get to that once we actually do analysis. because all these analyses will to some extent be, if we do analysis, we do descriptive statistics and we do frequencies for sex of the child, this, age of the mother, status. So once we do these analyses, you basically get here the syntax. So this syntax essentially you can then you can essentially copy it or you can transfer it automatically. But once you save it in your syntax, you actually save your analyses. So if I would now, this output file, you can save the output file. That's one way to go about it. So you get here a log that essentially you can use and store. So you can save this as an SVO file. So you can save, or SPV file, sorry. So you can basically save the output. That's one way how to save things. As another way is to essentially, you save the syntax. So as said, I prefer programming things because it's kind of easier for you to go back to each step of your analysis. And this you can also do with SPSS, where you have the possibility to save this, and hypothetically you could also learn how to program it, although it's a little bit of a complicated syntax to learn. But essentially you have frequencies, you have variables stated here, separated here by a space. No, not this. You can hypothetically, you can go into variable view and you just look for the name of another variable. You have here another nominal variable and you want to add smoke. It's the smoke. Now you just rerun the whole thing. Oops. And you just rerun that snippet. So you will get now smoke during pregnancy as an additional variable. So this is actually where you can use the syntax, and I would highly recommend you kind of get comfortable with the idea of having a data file open, an output file open, and the syntax open, because by that you get here an overview. This first line here essentially is get the file. This is naming the data set. This will be the frequencies. Then you can go back and you can do make graphs. Let's say we want to make a histogram. You can basically build histograms by just taking sex, age. Let's do age. There we go. This here. Okay. So we're doing now age of mother, and you basically can show age of mother on the x-axis. This should actually work, right? Or maybe not. No? Oh, very good. Simple histogram. So this is essentially your command to build a simple histogram, which basically allows you to just investigate here the age of the mother at birth. So this will be your code, which you just can paste, copy, paste. Now you put this here, and now you have the next command right here. Okay. So now you basically have your next graph here. So now you can reproduce this graph from your syntax within seconds. We don't want to save this. We're going to redo this whole thing by just using the syntax. So now just select whatever you want to run. I just run it. And this is redoing your analysis. So now let your just be innovative now to think about what the capabilities are of the software when you use syntax. You can basically run all these graphs and functions really fast and really very efficient. Okay, any questions to that? All right, if no further questions, well, we're on the top of the hour. I would love to have dinner. So I hope it was a little bit insightful and my explanations were helpful for you to understand. Let me know if there's anything else you want to discuss. There's some questions in the chat. What do we have? Okay.
Thank you so much for the review.
Yeah.
Yes,
Well,
very
let me know if you want anything else. Please utilize the discussion board. I think this is really most important, particularly with these asynchronous classes. So thank you, Caroline, for posting, and please don't hesitate, because every question should be asked, and both me and Sarah, we really wanna make this a good educational experience for you, despite the asynchronous virtual character. I think we can do a lot, and we can really bring this to a very good outcome. All right. Then have a nice evening if no further questions, and I'll try to get one again scheduled for next week.
Thank you. Have a good night.
Thank you.
good.
You
Good
too.
night.
Good night.